Yeah, so NMR is really interesting because at the heart of it, it's very fundamental analytical chemistry. And a battery, when it's cycling, most importantly, so when it's under its standard operating conditions, current is flowing through electrodes, ions are diffusing from one electrode to another. It's a very complex system. You've got, as I mentioned, liquid state ion diffusion occurring. You've got half-cell electrochemical reactions occurring. You've got mechanical factors at play. And then on top of that, you have the standard operating conditions of pressure, temperature, and how quickly you're cycling the battery. All of these affect the chemical reactions that occur at the interfaces in the cell itself. And NMR we view as a very powerful tool because right now we understand what we're putting into the system when we assemble the battery. We also have a very clear understanding of the operating conditions those reactants are experiencing. Again, temperature, pressure, cycling rate. What we do not have as detailed of an understanding is what's happening to those reactants in an intermediate phase. Once they form the layers we suspect they will form. And those layers are largely precipitate products. What about the soluble products that go back into solution as a result of those reactions? So we firmly believe that understanding those reactions on a very fundamental level is something NMR can help us with. And once you understand those reactions, you can start to optimize the chemistries and the cycling rates to induce the formation of layers that you desire and ultimately create a cell that cycles for a long period of time.